Hello, welcome back to Learn Physics. In today's video, we are discussing about oscillation. That has already we discussed about the oscillation chapter in detail. There's a quick revision portion for your for just as a revision for your exams. Okay, exam oriented. As I told in my previous videos, this is not in this video I won't be explaining about all the derivations and all in detail. Okay, just content I will tell and go, and if you have any doubt you can go through that playlist itself. I am giving it in the description box. Okay, so you can just go through that. So shall we continue? So oscillations, in that first we learned about the periodic motion. What is meant by a periodic motion? Motion that repeats after regular interval of time. Motion that repeats. Motion that repeats after regular interval of time. After regular interval of time. That is called a periodic motion. Okay, what is meant by oscillatory motion? Oscillatory motion means it's a to and fro motion. To and fro motion, that is called, or back and forth motion is called a oscillation. Oscillation is a to and fro motion or back and forth motion. Okay, so periodic motion means it will be repeating after a regular interval of time. Going, coming back, that is called a oscillatory motion. Next is harmonic motion. Okay, so harmonic motion means motion that can be represented as a sine function or cosine function. Motion which can represent as a sine function or a cosine function. That is called a harmonic motion. Next is simple harmonic motion. So what is meant by a simple harmonic motion? It can be represented as a sine function or cosine function, or we can say the force acting on that kind of motion will be directly proportional to the displacement. Okay, so then that kind of motions are called as simple harmonic motion. So it is directly proportional to the displacement from the mean position. Force acting on an object is directly proportional to the displacement from the mean position. So what will be the difference? See, now what is meant by vibration? Here another one, vibration. Vibration means that also a to and fro motion only, right? It's a to and fro motion only. Vibration also a to and fro motion. So what is the difference between an oscillatory motion and a vibratory motion or oscillatory motion? What is the difference between these two? Oscillation means, see, like this. That means one oscillation to the time required to complete one oscillation is more, but in time required for a vibration will be very less. Okay, that means if frequency is number of oscillations in 1 second, that is called a frequency. Frequency is more, then we can say it is vibration. If frequency is less, in 1 second if the number of oscillation is less, then we can say it is frequency less, then it is called a oscillation. Oscillation and vibration. Oscillation means frequency will be less, vibration means frequency will be more. Okay, now how we can represent this periodic motion and this oscillatory motion and all, or a simple harmonic motion in a mathematical way? Or I told already, it's a harmonic motion can be represented as a sine function and cosine function. So that expression you should study, then only we can do it will be useful for our numerical part. Okay. Next is what is meant by period. Period of oscillation means it is the time required to complete one oscillation. What is the time required to complete one oscillation is called a time required for one oscillation. That is called a period. capital T. Unit is second. Okay, time required for one oscillation is called period. Unit is second. Next is frequency. What is meant by frequency? Frequency is the number of oscillations in 1 second. Number of oscillations in 1 second is called frequency. Representation is nu equals 1 by t, or we can write f also. That is also okay. It is unit is formula is nu equals 1 by t. Unit is second to the power minus 1 or hertz. Hertz, we will explain that. Okay, so next is amplitude. Amplitude is the maximum displacement of the wave or oscillation, maximum displacement from its mean position. Displacement from mean position, that is called a amplitude. Amplitude is the maximum displacement from the mean position. Then next is angular frequency. Frequency represented in angle, that is called angular frequency. Okay, angular frequency representation is omega. Omega equals 2 pi into nu, or we can write it as 2 pi by t. Angular frequency. Unit is radians per second. SI unit is radians per second. That is angular frequency. Okay, so time period, frequency, amplitude, and then angular frequency. Okay, now we are going to find out how we can represent a periodic motion. Okay, periodic motion means motion that repeats after a regular interval of time. See, suppose a function f of t is there, that will be repeating after a particular interval of time. Suppose t is the time period which is in which the function is repeating. So f of t will be equal to f of t plus capital T. Okay, after a particular interval of time. Here what is the interval of time? Capital T is the interval of time. In that time interval, the function is repeating. The function is repeating, or periodic function is repeating after a particular interval of time. Okay, so here we can write it as f of t can be represented as a cos omega t, or it can be represented as a function of periodic function can be represented as the sum of a cosine function and a sine function. Like that also we can represent. Okay, so periodic function can be either represented as the sum of a cosine function and sine function, or it can be represented as a sine function or a cosine function. Okay, clear? This is how we will be representing a periodic function. Okay, so in the normal videos we already did the numerical based on that, whether it is a periodic function or not. Okay, such kind of questions are there in the textbook. Please go through that. Okay, so next we are going to study how we will be representing a simple harmonic motion. So already we told what is a simple harmonic motion, where force is directly proportional to the displacement from the mean position. Then that kind of motions are called as simple harmonic motion. That kind of harmonic motions are called as simple harmonic motion. Okay. Now next is how we can represent an SHM as a mathematical function. So x of t equals a cos omega t plus phi. A cos omega t plus phi is the representation of simple harmonic motion. Simple harmonic motion can be represented as x of t equals a cos omega t plus phi. So suppose if it is a sine function also, it is correct only. It's not mandatory we should represent it as a cos function. We can represent it as a sine function also, where a is the amplitude, omega is the angular frequency, omega t plus phi. This is the phase term. Okay, and phi is the phase constant. Okay, phi is the phase constant. A already we know it is amplitude and omega is the angular frequency. Okay, this is the representation of simple harmonic motion. Now we already learned how we can represent the simple harmonic motion in a circular motion. So if I am considering a circular motion like this, okay, so O is the center. From here, let P is the point. Okay, after a particular interval of time, so it's moving in, see this is y axis and this is x axis if I am considering, and this one x dash and y dash I am considering. So P I am considering, P is a point over here, so its position is x and y. Okay, so its projection is happening over here. First one I am taking P1 and this is the projection in y axis. So P1 reached here after a time interval, P1 reached to P2. So it is going to second position and this will be the second projection is here. And then same way it is moving in such a manner and reaching here. This is third position which I am considering. So here the projections are on x-axis is here, projection is y-axis is over here at the same position. Okay, so after a particular interval of time it is repeating, or the same way if it is coming like this, y-axis while I am considering it is moving like this, so it will be oscillating in this way. Okay, clear? So here it is fourth position is this one, fifth position is this one, here it will come, sixth position here it will come. So while it is moving from x to x dash, it is like this, the movement is O to y and y to O. Oscillation is happening, okay, in a particular interval of time. Okay, so that kind of motion we can represent it as a simple harmonic motion. That is how the projection of the particle in a circle, or projection of a particle which is moving in a circular path will be can be represented in an SHM. Okay, so a projection of a particle which is moving in a circular path can be represented as a simple harmonic motion. Okay, clear? So this is about the SHM. So next is, already we told x is represented as displacement, can be represented as x of t equals a cos omega t plus phi. Now how we can represent velocity here, that is a derivation part only. So already we did how displacement, if we are differentiating once with in displacement we will be getting the velocity. So velocity will be equal to minus a omega cos omega t plus phi. Minus a omega sin omega t plus phi. So that is the representation of velocity, or we can write it as this one, we already know it is a omega into 1 minus cos square omega t plus phi into square root, under root. Okay, root of 1 minus cos square omega t plus phi. So here I am taking this omega square inside. So a omega square minus omega square, omega I will take it outside, a I am taking it inside. So a square cos square omega t plus phi. This is under root. Okay, so minus omega into root of a square minus, what is a square minus cos square omega t plus phi? That is x of t, so x square. So in this way also we can represent the velocity function. For that you should know the trigonometric function, then only you can solve it in such a way. Okay, minus a omega sin omega t plus phi can be represented as minus omega into root of a square minus x square. So in the numerical part, if the you should consider velocity like this or like this, depending on the terms which is present in our equation. Okay, in the question. Okay, v of t equals minus omega a root of a square minus x square. That formula also you can use, or you can use minus a omega sin omega t plus phi. Then how we will be finding out the acceleration? Acceleration is minus omega square x of t. This is the representation of acceleration, that also a negative quantity only. Okay, now minus omega square x of t acceleration, then force, how we can represent minus m omega square x of t. But in the case of a string, if I am considering, f is equal to minus kx as per Hooke's law, F is equal to minus kx. So if I am comparing these two equations, k we will get it as m omega square. So the k will be equal to m omega square. So omega equals root of k by m. Okay, then time period of a spring, how we can find out? Capital T equals 2 pi by omega, that is equal to 2 pi into root of m by k. Okay, this was because divided by omega, taking the reciprocal and multiplying 2 pi into root of m by k. This is the representation of period of oscillation of a spring. Okay, period of oscillation of a spring. So movement of a spring also a simple harmonic motion only. Next we can consider simple pendulum. How we can find out the period of oscillation of a simple pendulum. Okay, period of oscillation of a simple pendulum. Okay, so what is a simple pendulum? Simple pendulum from a rigid support, a string with a bob. Okay, so a string with a bob, that is represented, that is a simple pendulum. So while it is taking for oscillation, say this is oscillatory part, here mg will be acting exactly downwards, tension will be acting in this direction. So while we are considering the mg, we are dividing it into components, we will be getting mg cos theta and this is mg sin theta. Okay, so mg sin theta and t will be getting cancelled and here it will be under rotational motion. So what will be that rotation force, torque acting on the system? That is equal to R cross F. So if L is the length of the pendulum, length of the pendulum means from the center of the ball to the fixed position, that is length of the pendulum. Okay, from the center of the ball to the fixed position, 2 is equal to mg sin theta into L, that is acting in the opposite direction, so it is minus. Next is 2 equals I alpha, this also we know. So since both are 2, we can equate that one and find, substituting the value of I. This derivation and all I already given you. Okay, minus mg L sin theta equals I alpha. Okay, so since theta is small, since theta is very small, we can consider sin theta nearly equal to theta minus mgl theta equals I alpha. But I, we know that it is ml square, so we can write it as minus mgl into theta equals ml square into alpha. M will get cancelled, 1 ll will get cancelled, alpha is equal to root of g by L theta. Okay, that is acceleration is equal to g by L into theta. So we know the force acting on the system, acceleration equals minus omega square x of t. So in terms of, here also negative sign is there. In terms of acceleration, this is oscillatory motion considering, right? So what is omega here? Omega square equals g by L or omega equals root of g by L. So what is the time period? T equals 2 pi by omega. So 2 pi into root of L by G. That is the period of oscillation of a simple pendulum. Period of oscillation of a simple pendulum, T equals 2 pi into root of L by G. Okay, clear? So now one more thing, energy of a simple harmonic motion. How we can find out? In a simple harmonic motion, we will be considering the kinetic energy as well as the potential energy. Kinetic energy means it is half mv square. So here you should apply the velocity of a simple harmonic motion. What is the velocity of a simple harmonic motion? Minus omega into a into sine omega t plus phi. That one you should apply here, and potential energy is half k x square. X, instead of x you can substitute it as a cos omega t plus phi. Okay, while you are substituting these two and adding the total energy. Total energy means potential energy plus kinetic energy. So you will be getting it as half k a square. Like that you will get the answer there. Sine square x of t, sine square omega t plus phi and cos square omega t plus phi will become 1. So you will get it as half kx a square. A is the amplitude, k is the spring constant. Total energy will be equal to half k a square. Okay, so this is about the total energy of a simple harmonic motion. Okay, so next we are going to study about the damped oscillation. What is meant by this damping? Damping means it is a what is that? If I'm giving a force and making it into an object into oscillation, so it is oscillating, right? So while it is oscillating, after some time it is coming to rest position. What is the reason? Because of the air resistance and the dissipative forces which is acting there. Viscous force, all those forces can act on the object, isn't it? So that is why the amplitude is decreasing. That is called a damping. Amplitude of oscillation is decreasing as time increases. So that is called a damping. Their damping depends on the velocity of the particle. Okay, so to provide or to avoid this damping, what we can do? We can apply an external force. That is called a forced oscillation. Forced oscillation means we have to avoid damping. We are applying an external force. That is called a forced oscillation. Okay, clear? So forced oscillations are the oscillation which is maintaining, the amplitude of oscillation is maintaining because of the externally applied force. Okay, clear? So that is called a forced oscillation. And when the natural frequency of the object is equal to the externally applied frequency, then it will be vibrating with its maximum amplitude. Okay, so that is called a resonance. Resonance is when the natural frequency is equal to the externally applied frequency, then that is called a resonance. Okay, clear? So that is about the resonance, forced vibration and the damped oscillations. Okay. So resonance, we have some examples for resonance. So usually the soldiers, the march past of the soldiers won't be happening there and on the bridge, because while they will be going out of order while they are marching in the bridge. The reason is, while they are marching, the natural frequency of the bridge can become equal to the frequency of the externally applied frequency. So the chances are there to break because of resonance. Okay, and another thing, earthquakes. While earthquakes are happening, all the buildings are not getting damaged in the same manner. The reason is, whichever building which is having the frequency which is equal to the frequency of the earthquake, so that will be completely destroyed. Others will be remaining there, or with a small damage they will be remaining there. Okay, so these are the important concepts in this chapter, and study properly. So while I am explaining that one, you will feel it is a very small chapter, but it's not like that. All the derivations are very important, and the other parts, what is that, other external questions also important only. So now you know only one more chapter is left out for our quick revision, that is waves chapter. Waves chapter is left out. So after completing that waves, we will be starting with some of the important questions. Okay, important questions means all the derivations are important only. So important questions and how we can deal with the small 1 mark, 2 mark questions. Okay, so I think it is clear for you and it is useful also, I guess. If you have any suggestion, you can give it in the comment box. Okay, and if you like the channel, please don't forget to subscribe. Thank you for watching. Bye.